Hi everyone, in this video we are looking at section 7.3, assessing normality, and we are going to create what is called a normal probability plot. First, what is it? Well, it's a graph that plots observed data, so it's recorded data, and it plots it against a normal score. So we're going to find what a normal score, and that's going to be the y-axis. The observed data is going to go on the x-axis. Okay, a little bit more on the normal score. That is the expected z-score, what we expect it to be for the data value, assuming that the distribution of the random variable is normal. Okay, so it's if the data comes from a population that's normally distributed, it's what the z-score should be. If the data comes from a population that's not normally distributed, then it's gonna look weird, and we'll define weird in a little bit. So the expected z-score of the value depends on the number of observations in the data set also. So the more observations, the will have varying z-scores, and we'll see what that looks like as we go through the process of creating one. So the steps that we'll go through to create our normal probability plot, we have a little bit of work to do ahead of time, and we'll kind of arrange that nicely in a table. We put the data in ascending order, so it needs to be in order. We compute f subscript I, and that corresponds to this formula here, I minus 0.375 over n plus 0.25. That's a really arbitrary and abstract formula. We don't delve into where it comes from in this course, but a little bit more on what it means on the next slide. It doesn't even really have a good name, but I'll explain what it means on the next slide. And then step 3, we're going to find the z-score that corresponds to that f sub I, and then we plot the observed on the horizontal axis, the observations, and we plot the expected z-scores on the vertical axis. And then we interpret all of that work, and the conclusion that you draw is that if the sample is taken from a population that is normally distributed, it is, then the normal probability plot of observed versus expected z-scores will be approximately linear. And when I talked about looking weird before, if it comes from a population that's not normally distributed, it won't be linear, or won't even be close to linear, and we'll see what that looks like later on. Now, in this slide, a little bit more on what that f sub I means from the previous slide. So the idea behind finding the expected z-score, if it comes from a population that's normally distributed, if our data comes from that, then we can predict, we use that f formula to predict the area that should be to the left of that score. So if it's the second lowest data point, a certain amount of area should be to the left of the score. If it's the third highest data point, then a certain amount of the area should be to the left of that score. That's kind of what that F value means. And you don't need to worry about like the formula or memorizing or anything like that. Just understand that that's what we're finding here. Now let's look at an example where we actually get to do a little bit of math. In this example, we have 6 data points. So there's 6 data points, 1, 2, 3, 4, 5, 6, and they represent the finishing time in seconds for 6 races of a greyhound in the 5/16 mile race. I don't know if anybody watches dog racing. I do not, but that's what this data comes from, finishing times in a race. And what we want to find out is that variable normally distributed? So the way that we're going to do that is create a normal probability plot and take a look at what it looks like. Does it look approximately linear? All right, and our steps that we'll follow from the other slide. First, I'm going to write down, I'm just going to number my observations. So I'm going to have a table and it ends up having, 4 columns. The first column is the index. All right, and that's just literally numbering the entries 1, 2, 3, 4, 5, 6. And then second column in my table is the observations, the observed values. So there's index, observation. So these need to be in order, so just make like a note of that. The smallest of those 6 numbers is 31.26, and then next we have 31.35, and then 31.91, 3206, 3237, and 3252. 32.52 is my last of the 6 entries. All right, so that's column 2. Now column 3, this is where we compute f subscript I. So I'm going to put some of them off to the side here, some of the substitutions off to the side here. The formula was I, or f sub I, equals I minus 0.375 divided by n plus 0.25. And now notice that formula does not at all rely on the actual observations. It only relies on where they fall: first, second, third, fourth, fifth, and sixth. So that's an important thing to like kind of pay attention to. Okay, so for the first one, we'll have f sub 1 equals 1 minus 0.375 over 6 plus 0.25. And that, if you type it into your calculator, is 0.10, 0.10. The second one, f sub 2, only one thing changes up in that numerator. It's 2 minus 0.375 over 6 plus 0.25. And when you're typing that into your calculator, parentheses around the numerator, parentheses around the denominator, or do the addition and subtraction first. Kind of up to you. Type that one into your calculator and you get 0.26. And I'm not going to write the other ones out. All that happens with each other substitution is that top number changes 2, 3, 4, 5, and 6. And what you end up with is the next one, 0.42, then 0.58, 0.74, 74, and 0.90. And there's our 6 entries there. And now let's recall, what do those represent? Those are the areas to the left of each of the 6 data points, or what the area should be if the data is normally distributed. So our fourth column in this table, and then we get to create the actual plot. The fourth column is the expected z-score. Expected z-score. So for that, if I have an area and I need to find a z-score, well, we're going to go and use table 5 that you were introduced to in the previous section. That's going to get used a lot as we go through the rest of the semester. So let me go down to table 5, and what we need to find, here it is down here, and I think I should probably zoom in on it. This is just a portion of the table. There we go. And if you remember from the work above, the first number, the first F1 was 0.10. So what I need to do is inside of my table, let me get my pointer here. There it is. I need to find 0.10 and what z-score corresponds to that inside of the table. Okay, so I start at the top in the center, go down until I get close to 10%. There's 0.009, 0.1 is 1%. Keep going down, keep going down, keep going down. Oop, there's 10 right there. So 0.1075, that's close to 11%. If I look to the left, I get higher. If I look to the right, we get a little bit lower. 1020, 1003. That's pretty darn close. So I'm going to go to the left. Actually, let me get my highlighter now. So I'm going to go to this guy here. 10, that's not a highlighter. There we go. 1003. Trace that over to the left, and I get negative 1.2 for the z-score, and then go up to the top, and 8. So negative 1.28 is the z-score that goes in my table up above. Z equals negative 1.28. But let's find one more just for good measure. Let's go to my F2 was 0.26, 0.26. Oops, that's a 6. There we go. So I got to scroll down a little bit more on my table. And if we try our best to find as close as we can to 0.26, go down a little bit more. There's 20%, 22%, almost 23, and 2. Oh, there it is. 2611. Go to the left, you get higher. Go to the right, you get lower. That's further away. So we're right there. That's why I said starting in the center is usually a good bet. So I'm looking here. Oops, want my highlighter. There we go. 2.6. And I'm going to go over to the left here. Right there. Negative 0.6. And then you can't quite see the top. There we go. And go up to 4. So this next z-score for my F2 is z equals negative 0.64. All right, so those are the only two I'm going to show you by hand. The other 4 you can choose to find on the table yourselves now, pause the video, take a look, pull the table up in MyMathLab, or your other option would be just to take my word for it. But I encourage you to practice more with finding z-scores on this table. You're going to need it. All right, so going back up to my table. There it is. So filling in my expected z-scores that I got by going down to the table 5. The first one we had was negative 1.28, then negative 0.64, and then the other 4 that we didn't look up, negative 0.20. And then what's interesting about this is the top 3 are all the same, 0.64, and that is what should actually happen, 1.28, all the same but positive. All right, so there's our expected z-score. Now that we have all that work completed, we can create our normal probability plot. And so that's what I'll put down here. And I'm going to title my normal probability plot expected time versus z-score. All right, and let's draw our axes. We've got a y-axis, and we have an x-axis. On the x-axis, this is the time in seconds. And then on the y-axis, it's the expected z-score. Expected z-score. All right, now for labels on the x-axis, you can see that the data points go from 31, a little over 31, to 32 and a half. All right, so maybe I draw my scale and go by 0.2s. That one sounds good. 31.2, 31.4, 31.6, 8, 30, there's 32.0, and then 32.2, 32.4, 32.6. On the vertical axis, we're going to do something just a little bit different. I'm going to put on the vertical axis 0 in the middle, because with the z-scores, if you look, we have positive and negative values. So we're going to have 0 as like a midline there, and then I'm going to go up to 1.5 above it. Oops, right there and right there. So this would be 0.5 and 1, and then down to negative 1.5 below it. Negative 0.5, negative 1, negative 1.5. Okay, so that's how I like to set up this expected time versus z-score probability plot. All right, and so now we take our data, which you can still see on the top right there. The observations go in the x, and the expected z-scores go on the y. So my first point is 31.26, and I go up to negative 1.28 would be about there. Oops, not a highlighted dot. Let's do a regular dot. Negative 1.28 would be about there. And then 31.35 is right about here. Negative 0.64 is right about there, I think looks good. Maybe a tiny bit lower, but we'll go with that dot. 31.9, so we're moving over a little bit to the right now. And negative 0.2 is a little bit higher. We'll try that just a tad higher. Then 32.06, just a little bit to the right of that, and positive 0.2, maybe about there. And then 32.37 up here to 0.64. And then 32.5 up to positive 1.28 would be about there. Now, if you have lined paper, I would hope that yours looks much better than mine. But it's it's a sketch that I'm doing, on a white screen. So I wouldn't expect perfection here, but you should get a rough idea of what this looks like. And now, let's interpret. So, does this look approximately linear? I think so. It looks fairly linear to me. The dots are grouped together in pairs, kind of, and we could approximately draw a straight line through. Well, that one's not very straight, but we could draw a straight line through those points and get pretty close to all of them. So yes, it's approximately linear. And what does that mean? Yes, this comes from a population that's normally distributed. What is this? The greyhound finishing time, the variable finishing time, is approximately normal. So that's the big conclusion that we draw with this one. All right, and with this last example here, it's already done for us. I'll just kind of reveal it slowly as we go through. We have the wait time in minutes for a roller coaster and 100 randomly selected riders. And what we want to look at is it normally distributed? And so you can't really tell just by looking at the raw data. There's a lot of numbers there. There's 100 of them. So what can we do to tell if we're normal? Because we have a lot of data here, one thing that we can do is to look at a histogram. So if I pull this box down a little bit and we look at a histogram, and we can say, whoa, it is not normal at all. In the previous example, we only had 6 times. Those 6 finishing times were not enough to get a good look at our distribution, right? That a histogram would be just pretty basic. It'd be like 2 bars that differ in height, or maybe 3. So with 100, though, we can get a much better view of the distribution from the histogram, and so we can see that it's skewed right. And you can think for yourself why that might be the case for a roller coaster. Why would it be skewed to the right? Sometimes you get on quick. Sometimes you have to wait a really long time, but there's definitely that minimum. Nobody waits less than 0 minutes. All right. But what we would see in the probability plot is down at the bottom here. And if I take this off and let me zoom in on my probability plot a little bit, this picture is not the best, but that's okay. What we see in the probability plot, this is created in Minitab, and I'll have a follow-up to this video with some information about doing this in Minitab. But you can see there is no way that distribution is approximately, or that this plot is approximately linear. There's like a wave pattern to it. It's a roller coaster in itself. But this is not approximately linear. So that's how, we could tell from the histogram absolutely up above, but this probability plot is in no way approximately linear. And so it fails that test. So the population is clearly not normal, not normally distributed. Okay, that is it for this section. Thank you for listening, and let me know if you have questions.